If you recall, we've been talking about applications of the derivative, the normal things that we do, make linear approximations, use the derivatives to maximize functions. And then we came across this, the gradient, specifically the gradient in a plane. Next section, it becomes the gradient in space. And it's a function of x, y, and z. And I give you exactly one chance to figure out what the gradient looks like if it's a function of x, y, and z. Just, you'll get one chance. If not, whole class is canceled. Here are the things that we want to remember about the gradients. So the gradient of f is a vector bears repeating, it's important. The gradient is a vector that indicates the direction of maximum increase of f. If you want f to increase the most, you go in the direction of the gradient. We said this another way by saying that the gradient will be perpendicular to the contour. So the gradient will be perpendicular to the contour. These two are saying the same thing. That meme from the office, they're the same picture. The contour indicates where the function is constant. So a contour is all the places where the function has one value. So it makes sense that the maximum increase is perpendicular to where there is no increase. So if we have a contour, if we walk along the contour, f is not changing. Contour is where the function is constant. So if at any point we're walking in the direction of the contour, the rate of change of f will be 0. The gradient will be perpendicular to this. That will be the indicate the direction of maximum increase. So if we are tangent to the contour, no change in the function. Perpendicular to the contour, maximum change in the function. That is the steepest direction up the hill. And that's how we were thinking about this yesterday. The steepest direction up the hill. So let's suppose we have a function. Let's use our standard easy function to think about, a nice hill, a circular paraboloid with a point 0, 0, 9, and then just falls down in ever increasing circles. Yeah. So our gradient of f, we need our two partial derivatives. Fx at xy is minus 2x, and fy of xy is minus 2y. So our gradient is minus 2xi minus 2yj. Let's pick out a particular contour. A contour where f of xy is equal to 0. If f of xy equals 0, then 9 minus x squared minus y squared equals 0. We're dealing with the circle x squared plus y squared equals 9. So we get a circle of radius 3. Centered at the origin. I make x go positive because this is, for me, the quickest variation of this. I need to spin it a lot less if I just use this orientation. So down is positive x and right is positive y. And coming straight out the page is our positive z. So I'll draw it here. I only have a 2D camera, so you can't see it. I actually only have 2D pens, so look, if I tilt this up, you can't see it coming out either. I know Mark Zuckerberg has some things to say about this and be like, oh, but if you have this class in Meta, actually, sorry, that's not what Zuckerberg sounds like. If you have this class in Meta, then you would be able to represent this properly. So I go, yeah, but then we don't have to be on Facebook and nobody here is a grandma. So I don't know how that's going to work. I'm just kidding. Mark Zuckerberg isn't a robot. Although, imagine the movie I, Robot with Will Smith, and instead of the robots they had, they were just all Mark Zuckerbergs. And some people are like, oh, wait, that wasn't what the movie was? Oh, never mind. That makes sense now. See, I can get away with that because I'm beneath Mark Zuckerberg's notice, so I'm saying. It's not like he'll ever notice. So I'm going to pick a point where it's easy to see what's going on. So I'm going to pick this point, 0, 1. Remember, I made X go in, positive X go in the down direction, positive Y go in the right direction. Not correct, to the right. If I calculate the gradient of F at the point 0, 1, so let's calculate the gradient of F at the point 0, 1. I get -2 times 0I minus 2 times 1J. So 0I minus 2J. So this vector, 0I minus 2J, is going to point towards the origin. I just realized in the previous example, I used orange for the tangent and green for the gradient. And now I switched the gradient to orange. That's it. I ruined Christmas. No one is ever going to understand calculus in this room ever again. I'm just kidding. One student be like, oh, I'm red-green colorblind. I'm safe. Yeah. Zero, what? Oh, it should be 0, 3. You are correct. Thank you. So that changes. This is not going to be 0, 1. I want 0, 3. So I'll have 0 minus 6. Thank you. You found my carefully planned mistake. 0 points for you, minus 10 for everybody. Let's think about why this makes sense. Remember the thing that we're looking at. The shape that's why I picked the shape. It's a circular paraboloid, and the high point is 0, 0, 9. So our shape is a circular paraboloid. Draw the circle first. They're called circular paraboloids to tell you to draw the circle first. It's like a built-in reminder. And what do I keep trying to do? Draw the friggin' paraboloid first. So the reason that I picked this shape, because theoretically I'm sometimes capable of drawing it. But it's also easy to see where the gradient is going to point. We have this maximum point at 0, 0, 9. We have a global maximum at 0, 0, 9. So what we're going to want to do is at any point, if we want to go the steepest route, we face towards the origin and go up the hill that way. That is the steepest direction. The most direct direction, head towards that maximum that high point on our circular paraboloid. So it makes sense that we have a vector pointed towards the origin. Let's pick another point. Now I'm concerned because I already messed up 0, 3 instead of 0, 1. What would be the point? Let's grab another point. Let's say let's just put it at a 45-degree angle in quadrant 2. So how much is that going to be? If that's 3, these are going to the size of 3 over root 2? No, wait. You know I picked 45 degrees? Because these two have the same absolute value. So this point is at, I even have a trig class later on today, but that's okay. This point is at, let's say, minus c on the x. Oh, we're also not in quadrant 2. We're in quadrant 3. Minus c on the y. Because I can't figure out how to include the incorporate the square root of 2. Because I changed my radius to 3. Because I make bad decisions at 8 o'clock in the morning. Let's find the gradient of f at this point. So the gradient at this point is also at 45 degrees going the other direction back towards the origin. So our gradient at negative c is once again pointing back towards the origin because that is the steepest direction. That is the most direct line to that highest point on our circular parabola. So if we're standing on this circular paraboloid hill and we want the steepest way up, we turn perpendicular to our contour, which will face us towards the z-axis, and then we should just head up that way. Normally I put the z-axis in this point. So turn towards the z-axis and head there. No matter where we are, we should face that direction. Face directly at the z-axis, and that will be the steepest direction up the hill. That's what the gradient is supposed to tell us. Any questions? Things that we need to remember. The gradient, well, first of all, how to build it. fxi plus fyj. We start looking in space plus fzk. More importantly, what does it tell us? It tells us the direction of maximum increase. What's the steepest path up this hill? It's going to be perpendicular to the contour. This makes sense because the contour is where the function isn't changing value. So perpendicular to that should be the direction of maximum increase. If we multiply by -1, that will be the direction of maximum decrease. If we had a thing rolling down this hill, it would be rolling perpendicular to the contour in the other direction. Any questions? Is everybody okay? Part 2 of gradients. Notice that the gradient is some kind of combination between our two partial derivatives. And the way we interpret those two partial derivatives, how is f changing in the x direction? How is f changing in the y direction? It's the rate of change of the function in those two directions. What we're doing now is building a vector that combines those two directions. So the next place we want to go is think about what is the rate of change of the function in some rando direction, some combination of x direction and y direction. So we need to figure out a way to calculate how the function is changing in any direction. Right now, we only have the x direction and the y direction. We have derivatives for those. Here's visually what's going on. Fx, Fy, how much in the x direction, how much in the y direction. I wanted the standard x and y because it was confusing me in the last problem, obviously. But what if I have some other direction, b, which is some combination of x direction and y direction? What is the derivative of f in that direction? How much is f going to change in that direction? And what does the gradient have to do with it, if anything? I mean, obviously the gradient must have something to do with it, because that's why I just talked about gradients at the end of yesterday and the beginning of today. Spread out introduction to the gradient over 2 days. If gradient didn't have anything to do with this derivative any direction, I would have just opened with this, right? So we're still looking at the same kind of question. What's the derivative at a point? But instead of just saying in the x direction or in the y direction, in this weirdo direction, 2i plus 5j. I should have picked something with a rational. Oh, well, you know what? Square roots are fine. We're professionals. We can handle it. But you see why I should have gone with 3 and 4? Anybody see why I should have gone with 3 and 4? 3i plus 4j? Why would 3i plus 4j be better than 2i plus 5j? What's the length of 3i plus 4j? 5. That's nice. What's the length of 2i plus 5j? Square root of 29. Why do I care about the length of this vector? The reason that I care about the length of this vector is because I don't want the length of this vector. I just want the direction. I don't want anything to influence. All I want out of this vector is direction. So what do I want the length of the vector to be? I only care about the direction from B. I don't care about how long B is, and the length might start coming into things. The length might start making itself a part of this process, and I don't want that. I only want the direction. I don't want due north at 80 miles per hour. I just want the due north part. So what we're going to want is a unit vector in the direction of B. So I'm going to take V and divide it by its own length. And that will give me a vector with a length of 1. Once I include that in calculations, I'm not going to have the length doubling up our calculation, or in this case, square root of 29ing our calculation. This is how we make a unit vector. This is how we extract just the direction information. Two over root 29i plus 5 over root 29j is pointed in the same direction as 2i plus 5j, but it has a length of 1. So if I include it in some kind of multiplication, I'm not going to have to divide out the length of this vector. So the big question is, how do we take the rate of change of f? How do we find the rate of change of f and see how f is changing in this direction? You have to make it a unit vector. There must be some kind of calculation involved because I said I don't want the length messing up our calculations. And this is so super organized, I can barely stand it. It makes so much sense, the calculation for the derivative of a function in a particular direction. It makes so much sense how we figure that out. once we see how it's supposed to go. It's kind of like a Sherlock Holmes situation. Once he explains how he comes to his conclusions, it all makes sense. For the most part, his observations are kind of based on luck, but that's more based on probability. He's just playing percentages. He's really good at it. And he just notices small details. And then afterwards, we're like, oh, wow, that was amazing. How did you come up with that? He's like, oh, well, I have a writer, and I knew what the answer was first. It's like when you see some test questions, like, oh, how are we supposed to know that? And the test writer was like, oh, well, the only reason that they know the answer is because they wrote the test. You know what I mean? It's like when your dungeon master gives you a puzzle, and after you see it, it's like, oh, well, yeah, it makes sense now, but it only makes sense from the answer working back. There's no way we could have got this from the puzzle moving forward. Do you know what I mean? Don't put those kinds of puzzles in your D&D game. Puzzles should be fairly simple and ultimately brute forceable. Unless you really don't want your players to go there or you really want your players' characters to die. You know what I mean? Is anybody here running D&D? That's going to be your next homework assignment. I'm just kidding. Just use top 3 puzzles. It is so organized. The way we take this direction and apply the rate of change of F in that direction once we get it down into a unit vector. Looking back, it's going to be so simple. And you're going to be like, oh, why didn't I think of that? So here's how it goes. Now, you can tell with that much buildup to tell you how to calculate the directional derivative of a function given some rando unit vector. You can tell that I'm not going to be telling you today because I want you to guess. This is going to be one of those things like, oh, it's going to make all this sense, but oh, darn, look at the time. I guess we're going to have to suffer. So I'm just going to skip all that bit, tell you that that's the bit that I'm doing, and tell you that we're going to have to suffer for a day. But I want you to think about how can I take the most recent piece that we had, the gradient, just-in-time information. Here's a key. It's going to open the next door that you run into, video game style, and this unit vector. How am I going to combine these 2 vectors, especially when I'm worried about multiplying by a length that I don't want? How am I going to take 2 vectors and combine them, especially when I'm concerned about multiplying by too much? That's going to do it for today. You can all tell me that answer tomorrow. I'll see you all tomorrow. Everybody have a good day, and thanks for playing.